Okay, so let's start. So in the last lecture, we looked at the weak or variational form. What we said is that if we take our differential equation and we multiply that by some weight function and then we integrate over the entire domain, what we're essentially doing is we're trying to satisfy the differential equation in a weak sense, right? It has to be equal to 0 for all functions w in some chosen space that then we define to be the energy space, right? So the energy space, as you can see here, is defined as all those functions that have a finite value of the strain energy, and the strain energy for this particular problem is defined here. We talked about that space. If we want to measure things in that space, we need a norm, right? So we define a norm, which is essentially the square root of the strain energy. And then we try to change the variational form, right? Because what we wanted to do was to balance derivatives, right? This is good because then it puts a less strict requirement in the type of functions that we're going to choose, right? So if you look at the differential equation here, you see that there is a second derivative on the displacement field. Now, if I reduce that requirement and then I balance derivatives, then I only need a first derivative of a function, and therefore I can already use linear polynomials, okay, to solve the problem. So then how do we balance derivatives? Well, we do integration by parts, and you see that immediately in the process of doing integration by parts, there is this boundary term that shows up, right? Which is essentially our boundary condition, the Newman boundary condition. And someone asked in Nota Bene, so I'm confused, who plays that question? Not here? Well, someone asked. And the question was, in Nota Bene, someone said, so I don't understand, you have Dirichlet and Newman boundary conditions in the same node. And well, the fact is that you either know the displacement, you can prescribe the displacement at the node, or the force. You cannot prescribe both, right? So you either know one or the other. But that doesn't mean that both do not exist, right? So if you know the displacement, you don't know the force, but the force is there, right? It's called the reaction force. And vice versa. Right? If you know the force, that means you're applying, let's say, a Newman boundary condition. You don't know the displacement, and that is essentially the outcome of solving the system of linear equations. Okay? So in the process, our boundary conditions arise naturally, and then we said, well, we can very nicely and very compactly write the weak or variational form as find some solution u in that energy space, so that the bilinear form is equal to the linear form for all those functions w in that energy space. And well, what constitutes the bilinear form? Everything that you have in your equations that are every term that depends on both the test function and the trial solution. Okay, the test function is our weight function w, and our displacement field is u. So you see here, this term has u and w, and this second term has u and w, and therefore both terms are part of the bilinear form, and everything that does not depend on the trial solution goes to your right hand side and is going to be the linear form. And you may say, well, but what about this term? This term here has u. Well, remember that the boundary condition is known. Okay, everything that is known goes to the right hand side. And so we looked at the properties of this bilinear operator. We saw that for the bilinear operator applied to u, then it's basically greater than or equal to 0, right? It is going to be equal to 0. Remember that this is going to lead to our stiffness matrix, the bilinear operator, and therefore it is going to be 0 in basically two cases. One is that you have either the trivial solution, u is equal to 0, right? Or that you have not restricted the rigid body modes by applying appropriate boundary conditions, and therefore your system is still singular, right? And therefore there's going to be an infinite number of solutions to that problem. The bilinear form, at least for these problems, is symmetric. So b of u comma w is equal to b of w comma u, and then you can apply the distributive property and so on. So these are some of the properties. And then we talked a little bit about what happens when you have non-homogeneous essential boundary conditions, right? How do we get around that? We talk a little bit about the spaces, right? The fact that for me to have a finite element, well, not in this case a finite element because we're not there yet, but if we have a function space, we said that there is this idea of closure of a space, that if I take two functions from that space and I add them together, or I subtract them or whatever, the resulting function has to lie in that space. And so there was this issue about functions that satisfy prescribed non-zero boundary conditions, because if I take two functions from that set that satisfy the boundary condition and I add them up, then that function is no longer in that set, right? So we have this issue, and therefore we thought about a way around it. And the way to solve that problem was basically to rewrite the solution as the sum of two parts, one v that can be taken from a space, and the other u tilde that satisfies the boundary conditions. Yeah. Finally, we looked at the Galerkin formulation, and if you remember, we said, well, so far u is an infinite dimensional, is taken from an infinite dimensional space, and then the moment we decide to take a subspace and then have n coefficients or degrees of freedom, then we assume that there is going to be an error, and this is basically our Galerkin projection. So we're projecting our differential equation into a subspace, right? And we saw that the Galerkin projection is picking the best possible solution from that subspace by looking at this orthogonality of the error. So in other words, if we go back to that equation, you can think of this expression here, right? As I'm multiplying some function w by the differential equation. So if the differential equation is actually not zero, it's some sort of residual, right? And therefore, by doing this multiplication and trying to set that equal to zero, what I'm doing is essentially projecting that differential equation into that subspace, right? I'm basically saying, think about the dot product between two vectors as an analogy, right? If I say, well, I have two products and I want that the dot product is equal to zero, those two have to be orthogonal, right? Well, something similar is happening here. If I take w and I take this differential equation and I say that those have to be equal to zero, that basically means that this guy here has to be orthogonal in the sense of function spaces to that subspace that is composed by all w's, okay? All right. So we did also the analogy in Euclidean space just to try to understand what all this meant. And now we are going to start talking about finite elements. Finite. So long to talk about finite elements. All right, let's get started. Okay. So say we're going to have our bar, and now we're going to discretize this by segments. And what we're going to do now is we're going to try to use very simple functions to represent the behavior in each one of those elements. So we can have, for instance, actually, let me draw an axe here. And then these are going to be my functions. These are the so-called hat functions. Yeah. and this is going to be a value equal to 1. And so this here is going to be phi1, phi2, phi3, phi4, phi5, phi6. These are the so-called hat functions. Yeah, well, and how do we write phi sub I is going to be equal to x minus xi, and I is essentially any node, xi minus 1, or xi plus 1 minus xi plus 1 minus xi. So you can immediately see when this is minus 1 here, right? So you can see that when x here, which is our variable, right? So xi and xi minus 1 and xi plus 1 are the locations of the nodes. So when x here is equal to xi minus 1, then this whole thing is equal to 1, right? When x is equal to xi, then when this guy is equal to xi minus 1, this whole term is equal to 0. When this one is equal to I, then that term is equal to 1, and so you have a linear function. And similarly here, right, when x is equal to I, then you have equal to 1. When this is equal to I plus 1, then you have equal to 0, and so you are in the other part of the linear function. And so these are the so-called hat functions or roof functions or tent functions. They have different names. Okay. Now these functions have a really nice and interesting property, and it's the fact that phi I of xj is equal to the Kronecker delta. So in finite element, this is called the Kronecker delta property. And basically it says that if you take any function and you evaluate it in a node other than where that function is defined, that is going to be equal to 0. If you take any function and you evaluate it in the node where that function is defined, that is going to be equal to 1. Yeah. Another nice properties of these functions is what we call the partition of unity property. So these functions that I'm using here form what we call a partition of unity. And that essentially means that at any point along that bar, if I add the shake functions, the result is equal to 1. And this is actually a very important concept that we use later in the next course, the enriched finite element course, because we use this partition of unity property a lot. Okay, we use this basically to localize the effect of enrichment functions, right? So if I take any function, say you have a singular function that goes to infinite at some point because you have a crack tip, for instance, and now I multiply that function with this type of partition of unity, essentially what you do is you're localizing the effect of that enrichment to the elements that form that partition of unity. Okay, we use this property a lot. Okay, so now that we have these functions, how do we express our trial solution for the finite element method? Now remember that we have subdivided the bar into little segments, and we assume that we have localized behavior, right? And so we're going to take our trial solution, and notice I am using the superscript h that denotes the mesh size. Okay, so we are already talking about a discretized solution. And I'm going to write it like this. So this is going to be my trial solution. Okay. Now, of course, just because of the Kronecker delta property, you can already immediately see that the degree of freedom, right, this UI that I put here, is essentially the displacement field evaluated at the location of the node, right? Because of this property, this Kronecker delta property. That is super nice because it attributes a physical meaning to the degree of freedom, right? The degrees of freedom, remember, that are coefficients that are scaling, right, the importance of the different basis functions, right? But if it just happens that at the location of the node, the function is equal to 1, like in this case, right, then the degree of freedom automatically tells you what is going to be the displacement at that location. This is a really nice physical meaning for the degree of freedom, which is, by the way, lost when we look at more advanced formulations. Right? When we see the P version of the finite element method, this property is lost, and it's only valid at the ends of each element. But inside you don't have this. So in enriched finite elements, you also lose this nice property. Okay, and now I'm going to take the wave function to be written in the same way. Yeah, and if you remember, if you take the trial solution and the wave function from the same space, do you remember how was this called? It has a name. So it's a Galerkin approximation, but who remembers how you call this from last class? Bubnov-Galerkin. Yeah? And again, choosing the functions from the same space has nice implications later on, because, for instance, what's going to happen? Yeah, we're choosing it from the same space. So what's going to happen later on with the stiffness matrix? Who said symmetric? Well, someone said symmetric. Yeah? All right. So if we write our Galerkin statement, if you remember, we said find UH in some subspace, and I'm using EH now, of omega. By the way, omega is, of course, my entire bar that I didn't put here. These are my element 1, element 2, element 3, element 4, element 5. And of course, this omega is a subset of, let's say, the reals, okay? Such that, well, the bilinear form is equal to the linear form for all WH in EH of omega. And by the way, I didn't put it here, but normally when you have a discretized domain, you also use H. In finite elements, omega and omega H don't necessarily have to be the same. So omega is your, let's say, your body, right? But omega H is usually used to denote the discretized version of that body. So normally what we do here, this was going to be omega H, and here as well omega H. But in the one-dimensional case, both are equivalent, okay? In 2D, that doesn't happen. Okay, but then let's replace what those are, and then of course we have, let's use J to 6, Vj, Uj, and so I have replaced in the bilinear form, I have inserted my the way we express our trial solution and our weight function. And if you look at it, this part of the trial solution or the weight function is known. We defined the shape functions already. So the only thing unknown is basically our coefficients, W or U, okay? So this statement that I have here for all WH in that subspace, just because we already know the shape function, translates to for all Wi, of course, that is a coefficient, right? And I is equal to 1, 6. In other words, they for all WH translate into having all type of coefficients, because the other part of that weight function is already known. Okay? All right, so we can work out a little bit this equation, so we can take this sum out. And then what you get is and again, I can do this because I can take out these are, remember, coefficients, so they can be taken out of the integral. And I'm going to copy this again. So if we group terms, what we have and well, this statement here, right? So if this whole expression has to be equal to 0, right? Since this equation has to be valid for all wi's, these are all coefficients, that essentially means that this whole thing here has to be equal to 0, and this is where we're getting our system of equations. So this essentially is going to translate into being my K matrix, and this here is going to lead to my force vector, and of course this is going to be my displacement vector. Okay, now of course you can take values of j equal to 1, and then you have one equation, right? So that's going to be essentially one row, and then you take j equal 2 and so on, and so this leads essentially to our system ku equals f. So I'm going to put here ku equals f, which we solve for our degree of freedom, and again I'm using uppercase U here to show that this is a vector that contains all the displacement of the nodes. Yeah? Yeah?
And then phi is here a function, right?
Shape function.
Shape function, yeah. And that is dependent on what like what body you evaluate.
Depends on the type of problem that you have. So we were talking about truss elements before, right? So essentially truss elements are also going to be working with these linear functions, yes. Right? So in the end, when you will see when we do the integral, you're going to end up having this EA over L and then a matrix 1 minus 1 minus 1 1, which is probably the matrix that you have seen in nonlinear mechanics. But what this basically means is that if I just replace that bar for anything, right, you are still going to be integrating shape functions. Remember that I'm not integrating directly the shape function, but the derivative. Remember how the bilinear form shows up. So this b of phi I, comma phi j, when you plug that in, you will see that you're applying the derivative of those shape functions, which are going to be constant. Okay, and you already see that. Remember that we lowered the requirement on the differentiation, right? That basically means that we can already work with linear polynomials because we can apply the derivative only once. Okay? So there is an alternative approach to get to the finite element equations, and I actually like to do both so that you see the same from different angles. So what I'm going to do now is I'm going to consider the equilibrium of one single element. Okay, and then after we do that, we're going to see what happens when we assemble the contribution of all elements, and then we are going to obtain the system of linear equations, Ku equals F, in a different way. So if we do that, well, let's consider of one element. And of course, when we talk about equilibrium, right, we're looking already at one element in the weak sense, right? Remember, we're far away already from the strong form of the problem. So if I take one element, let's say this is my element I, and this is node xi, and this is, let's call it xj. Could be I plus 1 as before, but let's say xj. And so the bilinear form for that one element, if you remember, is going to be EA, and then okay. So if we look again, remember that this was, I'm just rewriting the bilinear form, and all what you have here is the linear form. And if you remember the linear form, we had the effect of the load per unit length, right? And then you have the effect of the boundary conditions that again arise naturally. I'm going to move this. They arise naturally the moment we do integration by parts.
So is this the Vxi or Vxj or Uxxj?
Sorry?
The Vxi or Uxxj, the last row.
Not sure what you're saying.
WH xj times Vxj or Uxj.
This?
Yeah.
This is the axial force, huh? This is essentially what is n. Remember, n is your axial force along the bar, right? These two terms show up because of the boundary conditions. If you remember, we did the integration by parts. There was EA du dx, and that is essentially equal to EA du dx is essentially this axial force, right? Well, multiplied by the area. That's why EA. Okay. And therefore, this is basically the force on the right end of the element, and this one on the left end of the element. And that's why I say here xj, which is this node here, and then this one is xi, which is here. And I see that there is an issue when I move this stuff. Okay, that it's coming here. Okay, all right. Now, of course, there are only two shake functions that are non-zero here, right? Remember that we're using these hat functions. So who can tell me what are those functions? The only functions that are non-zero in this element.
Phi I and phi j.
Phi I and phi j, right? So of course, if I want to, we can plot them here. It's going to be something like this, and maybe something like that. Okay. Okay. So because in this element only these two functions are non-zero, then for this particular element only, you can write the approximation UH as, and let's say UH of x is going to be equal to phi I of x UI. Remember that UI is the degree of freedom, so these are coefficients. So whatever is a function of x is just the shake function, plus phi j of x uj, and you can express that in matrix form, and this is normally the way it's written in finite element terminology. So that essentially means that phi is a row vector that is multiplying a column vector, and therefore you get this phi I ui plus phi j uj. This is standard in finite element terminology. And then, of course, again, my weight function can be written in the same way. Phi, I'm using uppercase, right? Which is the same as having phi w uppercase W transpose and then phi transpose. Okay, so when we adopt this type of matrix notation and we plug back into our equilibrium of the one bar, what we get is something that looks like this. This is what we get. And now I have expressed my little equilibrium in the element in matrix form. And of course, remember that this expression for all WH, the moment we express what WH is, right, and we know the shake functions have some form, and then the coefficients are what is missing, then in matrix form, that is essentially saying for all vectors, right? And because we have only two shake functions that are non-zero, then that is valid for all w's in R squared. So it's basically a vector of dimension 2. Yeah? Okay. So, and the only thing I'm missing here I define the matrix B that in the finite element world is called the strain displacement matrix, because it's essentially linking strains to displacements. And for this particular bar problem, is essentially written like this. And so the for all W in R squared translates into having this, whatever is in the brackets is equal to 0, and that is essentially my KU equals F for one element. Okay? So what we get is essentially, I'm going to say it again, this statement for all vectors in R squared, because this expression, this whole equation has to be valid for all two-dimensional vectors. Then, well, if you group things on the one side and then that has to be equal to 0, that basically means that whatever you have in the brackets has to be equal to 0, and that is the KU equals F of your local one little element. Okay, so I'm going to just copy this. And then what we have here is, I'm going to use another color, this term here and this term here. So this is going to be my little matrix, stiffness matrix, and this is going to be my force vector. And so for the time being, what we have is KU. Remember that this U here is for that element as well, so I should also use UE is equal to FE. Yeah, for that element. And we call that element EI. Okay? Now, the behavior of the whole bar is then obtained by assembling the contributions of every single element. That operation is called assembly in finite element terminology. And normally it is denoted with an A. We have, well, tons of papers refer to what the so-called assembly operator, which essentially means you have to sum things at the right places. So you just add things for the corresponding degrees of freedom. That operation is called assembly. So in essence, what we do, we take one element, and then we obtain the contribution of the element neighboring to that element, and then the neighboring element, and you see that all these forces that are shared between elements are going to cancel out one another, right? And so the only forces that are going to be left without canceling are the ones at the boundary. And these are your boundary conditions for the whole bar. Let's write that down. And then we're going to take a break. So what we say is now uppercase K, which is the global stiffness matrix, is going to be obtained, and I'm not going to use a sum. Some people use a sum, but I'm going to basically use a different symbol. And I use lowercase k, KE. And well, if I use E to denote the element, I'm going to use then E as the index as well. And then the global force vector is going to be obtained as the assembly of the contributions of all local force vectors, FE. Yeah? Here, A is the assembly operator. Global stiffness matrix and force vector. Okay? And that's it. That's pretty much it. Remember, we derive the finite element equations in two ways. We use the bilinear form. We just plugged in the way we express the equations, and of course, those expressions are valid for the entire bar. And the second way is just to look at the equilibrium of one element and then considering what happens when you add the contribution of all elements. In both cases, you obtain the same equations. Okay? Any questions so far? Okay, let's take a break, and then we're going to have a short class on isoparametric mapping.